For this particular one, we're going to go over what happens with SPSS in doing this kind of data analysis. This is the first time that we actually have not tried this out by hand, but I wanted to show you actually how you would put this in, and next week in class we'll kind of go over this. In this case, you can see there are a total on the input screen of 3 columns. The first column is the dependent variable. Those are just all the scores. And the idea is, with the 12 scores we have, columns 2 and 3 simply represent the independent variables, the variables that I manipulated as the experimenter. And the idea is I put value labels in them so that we would represent all 4 different conditions. So I think I made alcohol, I made the number 1, no beer, and I made the number 2 with the 72 ounces of alcohol. And then for pills, the second independent variable, I made no pills, a 1. I made the 50 milligrams 2. And then if you look at the first 3 numbers, with the labels coming up, they're all in the no fun group, getting nothing. The second group is just getting the Xanax. You can easily see the mean is 80 there. The third group is just the alcohol group, another mean of 80 there. And then the final group is where they get both of them. And you can see in that particular one what the mean is 20 for that one. So that's actually how you do the data input when you show up to class next week. We'll make sure you learn how to do this for the 2-factor ANOVA. More importantly, though, is step number 4 is the data output. And I'll show you how to do this next week as well in the in-class session. But remember, we're trying to evaluate, are there 3 effects here? And so if you remember, the 3 questions are, is there a main effect of alcohol? Is there a main effect of pills? And is there a statistical interaction between alcohol and pills? So we actually get different sums of squares for those things. Actually, the sums of squares for alcohol, pills, and alcohol by pills, they all add up into something called the sums of squares between groups. Remember that from the 1-factor ANOVA, the sums of squares between groups? So now they're all kind of partitioned. That's the word we use into the sums of squares for the main effect of alcohol, the sums of squares for the main effect of pills, and the sums of squares for the interaction. Never use the term interaction in the same sentence as main effects. Don't use main effects and interaction in the same sentence. And finally, the bottom line is very interesting. It says the sums of squares for error. That actually stands in this case for the sums of squares within group. And let's actually start by figuring out how we get that number there, 108. Once again, if anything says error, which is the sums of squares within group, how do we want that number to be? We want that number to be low, don't we? So the sums of squares there within group is 108. Let's actually go back to the page that actually has all the individual data. It's very actually to actually get the sums of squares within group. If you go back to the situation where the 3 people got no Xanax and no beer, if I asked you to figure out the sums of squares within that group, what would the sums of squares be if the 3 numbers are 100, 100, 100? Well, there's no dispersion there, so the group mean is 100. So you would actually get sums of squares within that group being 0. So if you want to write that in somewhere, sums of squares of the no beer, no Xanax group is 0. Is that good or bad? That's really good. That means there's no dispersion in the first group. Let's go down to down the column to the second group, the 50 milligrams of Xanax. The mean for that group is 80, and then we have a 75 and an 85. Could you figure out the sums of squares within that group? Take just a minute or so, see if you can compute it. It should be pretty easy here. The mean, x bar, is 80. One score is 75, the other one is 80, the other one is 85, so it would be 75 minus 80, quantity squared. So that's 5 squared is 25, 80 minus 80 is 0, and 85 minus 80 is once again 5 squared is 25. So the sums of squares within that 50 milligram Xanax no beer group is, what, 50. And then if you go to the right, where it's the people who got the 50 milligrams of Xanax and the alcohol, 15, 20, and 25, the same amount of dispersion there, right? 15 minus 20 squared, plus 20 minus 20 squared, plus 25 minus 20 squared. The sums of squares within that group, 50. And then finally, 78, 80, and 82. You'd get that sums of squares within group, the mean being 80. And so the idea is 78 minus 80. 2 squared is 4. 80 minus 80 is 0. 82 minus 80 is 2 again, 4. So the sums of squares within that group is 8. So you've got 0, 50, 50, and 8. And if you add it all up and do the hokey pokey and turn yourself around, you would get the sums of squares within group being 108. So hopefully you can see that and figure that out. Let's actually keep going with the sums of squares within group. What do we do next? We figure out degrees of freedom within group. Degrees of freedom. How many people do you have in each group? 3 people. 3 minus 1 plus 3 minus 1 plus 3 minus 1 plus 3 minus 1. So it's going to be degrees of freedom 8. And then how does it come up with the mean squared within group? 108 over 8 is 13.5. So the variance within group is 13.5. Once again, how do you want that number to be? You want that number to be small. The smaller that is, the less dispersion you have within a group. For the people who got the drug or the alcohol, you hope that they're all close to the same numbers within that group. So the sums of squares within group is the 108. You have 8 degrees of freedom, so you have variance within group being 13.5. So that's the one idea. That's how you get the variance within group, the denominator for the F ratio. The other 3 F ratios, or the 3 F ratios. You get the 3 F ratios if you remember back to a 1 factor ANOVA. In a 1 factor ANOVA, the F ratio is equal to the variance between groups over the variance within groups. But now in a 2 factor ANOVA, it's a little different. We don't just have variance between groups. We have variance due to the A main effect, variance due to the B main effect, and variance due to the interaction. And so what we do here is we actually get the variance for the main effect of A, variance for the main effect of B, variance for the interaction, and then we put them each over the variance for the error, the variance within group, 13.5. So let's start off with this question of, is there a main effect of alcohol? Notice the sums of squares there, 4,800. The sums of squares are 4,800. What do you think? Do you want that number to be large or small? The idea is you want that number to be large. So for the main effect of alcohol, that idea was when you go back to the cell means, if you're looking at C here on the outline, the idea is you go down the matrix. For no beer, the mean was 90. With beer, the 72 ounces, the mean was 50. The more those numbers are different, the larger the sums of squares for alcohol will be. And in this case, it's 4,800. Notice the same number is computed, and I don't have to go through the details with you, on the main effect for pills. Once again, that just reflects the side numbers, the 90 versus 50 again. You want that number to be large. That means there's a lot of variation due to that particular sums of squares. And it's the mean of, or the marginal mean for no pills versus the marginal mean for with pills. Finally, how do you get the alcohol by pills interaction? That 1,200 there. Well, that number will be larger the more the lines are non-parallel. The more the lines are non-parallel, the larger that number will be. And so in this case, the lines are quite non-parallel, and that's where the sums of squares is 1,200. Next column, the degrees of freedom. Well, what are the degrees of freedom for the main effect of alcohol? Well, you got to say, well, how many levels of alcohol are there? There are 2, so there's 1 degree of freedom for that. How about for pills? There's 2 levels of pills, so 1 degree of freedom for that. And then to figure out the interaction, you actually just multiply the alcohol and pills degrees of freedom. They're each 1. 1 times 1 is 1. So the degrees of freedom for the interaction of alcohol and pills is 1. And then we already got the 8 before for the degrees of freedom within group, because each group had 3 people. 3 minus 1 times 4 is 8. Next, the mean squares. The first mean square. The variance, mean square, remember, is another term for variance. The variance for the main effect of alcohol. The variance for the main effect of alcohol is the sums of squares for alcohol over the degrees of freedom for alcohol. 4800 over 1. So the variance for the main effect of alcohol is 4800. Same thing for the variance due to pills, that's 4800. And finally, the variance for the alcohol by pills interaction is 1200. 1200 over 1. So we get the variance due to each one of them. Finally, the F values. The F values for each of these. Notice it said the F value for the alcohol main effect was 355. The question is, how did it come up with this? Well, the answer is it came up with this by taking the variance due to the main effect of alcohol, 4800, and dividing it by the variance due to the error, the variance within group, 13.5. 4800 over 13.5 is 355. Same thing for the pills. The main effect is 4800. 4800 over 13.5 is 355. And finally, the interaction, same thing one more time. It's how non-parallel are the lines, and the variance due to that, 1200 over 13.5, 88.89. I'll stop this one here and then wrap it up with significance.